Hello, I'm Jason Weiss from Oregon State University, and today I'd like to talk about shrinkage-reducing admixtures and their role in concrete science and education. I'd like to begin by thanking Rilem and the Education Committee for inviting me to provide this webinar today. What we're going to start off with here is a picture of a bridge deck, and this is a typical structure where you may expect to see shrinkage problems. One of the reasons for this is you have a very large surface area where evaporation can take place, and the concrete is usually fairly heavily restrained, which usually means that this is the type of structure that's very susceptible to cracking. So what we want to do today is we want to talk a little bit about shrinkage, and we want to get into some of the basics of shrinkage, but then really to start to dive into some of the things that shrinkage reducing admixtures can really bring to the table. First, the most important thing to talk about is that shrinkage is really a paste property. So when we actually start to get into this, shrinkage is a paste property. This means that it's the water in the cement portion of the system that's going to shrink. The aggregates themselves are going to restrain that shrinkage, and this has been known for quite a while. Where Layer Meat discussed this, and we talked about the idea that you could actually try to minimize the paste, and by minimizing the paste, you could greatly reduce the amount of shrinkage that's occurring in the system. Now, this was quantified by Pickett, this was quantified by Hobbs in the 50s and 60s, but a general rule of thumb is that for every 1% of paste that you remove for the system, you reduce the shrinkage by about 5 to 6%. So this is really a good first rule of thumb. If you want to try to reduce the shrinkage of the system, the first thing you can do is you can optimize your aggregates, minimize the amount of paste that's in the overall system. I think it's important that we start out that we mention that the papers that we were talking about just a few seconds ago by Lear Mate, he was one of the founders of Rilem, and in fact, Rilem's most prestigious medal is named after him. But he was also very active in the area of shrinkage. So I wanted to just draw that little bit of connection as we now start to move into the next topic. The second basic principle of shrinkage that like to draw our attention to is that shrinkage is really largely due to the capillary stresses that develop inside the pores. Now, there are several mechanisms that can be involved, but one of the things that I really like to motivate when I start to teach about the shrinkage of concrete is really the fact that the capillary stresses are going to be related to really two things that we have control over in concrete mixture design. Uh, the surface tension of the fluid, which is in the numerator, and the size of the meniscus that forms, which is going to be approximately equal to the size of the pore that's emptying. So the idea here is that if we want to reduce the capillary stress is going to be what's responsible for the shrinkage. We really can start to utilize the Kelvin-Young-Laplace equations, and we can really start to take advantage of this. So we can start to look at how the shrinkage is going to be impacted by the size of the pores that are emptying, and we can start to now look at ways to mitigate shrinkage. We can look at ways that we can essentially refill the pores. We can look at ways that we can alter the surface tension. So if we really start to get into this and we dig into this in a little bit of detail, we can see that as water leaves the system, the water wants to stay on the surface. The water wants to stay on the surface, and there's a stress that's generated in this fluid that results in the formation of this meniscus, and this stress actually pulls these silica sheets together. A very simple way of thinking of this is if you've ever seen glass slides and you've had a drop of water between those glass slides and you tried to pull them apart, it's really difficult to do. And the reason for this is because of the surface tension of water. So it really wants to pull those silica sheets together. And that's exactly what we have happening in millions and millions of gel pores as we work our way throughout the system. Now, the thing that's really important when we start to talk about the basic principles of shrinkage is the size of the pores are really going to be related to the capillary stress that develops. And the relationship is an inverse relationship. So, what this means is the great big pores, the capillary pores, really don't make a huge impact on the overall shrinkage. It's the gel porosity that makes a big impact on the shrinkage that takes place in the system. So the really important takeaway here is it's not the water to cement ratio necessarily that controls the shrinkage. It's the volume of the paste and more specifically the volume of the gel pores. So here we can actually see a calculation that shows us the volume of the gel pores from water to cement ratios of zero point 0.3 to about zero point 0.7. And what you can see is at the same levels of hydration, you have a very similar volume of the gel pores in the system and would have a very similar overall shrinkage. In addition, we talked about the fact that you could actually put something into the system that could actually refill these pores, and that would reduce shrinkage. And this is the concept of internal curing, either through a lightweight aggregate or a cellulose fiber or through superabsorbent polymer. And this is another area where Rilem is a very, very active group, really in advancing that science. Now, if we start to look at the capillary pressures that are developing, we have a very idealized system here where we have large pores going to smaller pores. And the basic principle is that the fluid leaves the large pores first. And as it leaves each one of these pores, we're going to be dealing with the capillary stress that develops at those pores. So again, for very large pores, the capillary stress that develops is not very high. So we wouldn't expect a very large shrinkage. But as we get to smaller and smaller pores, this capillary stress really starts to rise. If we alter the surface tension of the fluid, so let's say we're here with this size pore, if we reduce the capillary stress, if we reduce the surface tension of the fluid, we're going to drop the capillary stress pretty substantially. So here, if we drop the surface tension in half, we're going to drop the capillary pressure in half, which means we're going to drop the overall shrinkage to about half. Now, it's important to note that we can actually measure the surface tension of the shrinkage reducing admixtures. And here's an example of several of these shrinkage reducing admixtures. Concentration is shown along the x-axis where we're essentially replacing water with shrinkage reducing admixtures. So we have about a 5% reduction, 10% reduction, 20% reduction. And what we notice is after about a 15 or 20% reduction, we see that this has really plateaued and we've really reached a steady state value. Now, the real trick to looking at all this is we can actually start to look and zoom in on this axis by placing this on a log scale. And what we see on our right-hand side is the same information for just a pure water system and then for a system that looks like a pore solution. And what we notice again is as we add shrinkage reducing admixture to the fluid, we're going to reduce the surface tension and we can drop the surface tension substantially. We will reach a certain point where all of a sudden the behavior starts to level off. And this is really where we start to see critical micelle concentrations start to form in the overall system, where the molecules that are in the shrinkage reducing admixture really start to interact with each other and really don't have the overall behavior on the fluid that we really want them to have anymore. So adding more and more really doesn't reduce the surface tension any further. The big takeaway from this, though, is what you'll notice is that the addition rates are not linear with the addition of SRA. We see about a 25% reduction in the surface tension when we add 1% SRA by mass. By the time we've added 5 or 6% SRA by mass of the solution, we've dropped the surface tension to about half of the surface tension of water. Now, if we start to look at what that means in terms of the free shrinkage of the overall system, and what we've done here is we've essentially measured the shrinkage with different amounts of SRA in the pore solution, and this is just the SRA in the original solution, the surface tension with the SRA in the original solution. What we'll notice is we can measure the shrinkage of the system, and this is just a shrinkage of the paste in an expression here where we relate it to the relative humidity. There's a linear reduction in the shrinkage as the surface tension increases. So not surprisingly, the surface tension is going to be linearly related to the capillary stresses that form, and that's going to be linearly related to the shrinkage reduction that occurs in the system. So approximately what we can see is if we cut the surface tension in half, we're going to cut the shrinkage in half. Now, this is only part of the story. Because as I mentioned before, there are several mechanisms that are involved in shrinkage. And when we're at the very highest humidities, so when we're at the far right-hand side of this curve at 100% relative humidity, we're really starting to empty the largest pores first, and water is leaving the large pores. And what we're starting to notice is that we're seeing a shrinkage strain develop inside of these materials. Now, initially what we're seeing a lot of these capillary stresses that are forming in the system, and as we decrease the humidity further and further, we're going to be emptying out smaller and smaller pores. Well, we're going to get to a point in the system where all of a sudden the thickness of the water on the surface of the pore really starts to dominate the overall behavior, and the concept of having this meniscus really starts to diminish. So once we get to a point where we're starting to empty pores that are maybe 10 molecules wide, all of a sudden now this concept of bulk water in a meniscus really starts to break down. And if we do some calculations as to where that might be happening, we see that for a Kelvin radius of about 3 nanometers, for a shrinkage reducing admixture system, that would happen at about 80 or 83% relative humidity. And for a plain water system, that would happen at about 70% relative humidity. And so what you'll notice is as soon as the capillary stress mechanism starts to go away, we really start to see a deviation in the behavior, the shrinkage of these systems. So up in these larger points, this original line is really controlled by the capillary stress. However, as soon as we get to a point where we no longer really have these menisci that can form, we really start to see a deviation. This is where we see the fact that we're going to have a very, very different shrinkage with the shrinkage reducing admixtures. Now, an interesting aside is that many times we think about shrinkage reducing admixtures as being a chemical admixture that's mixed in with the fresh concrete. However, a lot of the early work really looked at this as a topical addition. So essentially, the idea would be that you would cast your slab and then you would essentially put your shrinkage reducing admixture on the top. This can be very, very effective, and we've actually evaluated this as well. And this can be very effective to reducing the shrinkage because what it's going to do is it's going to work on the pores very near the surface, which are the pores that start to dry first. In fact, if we kind of think about slicing a structure up into pieces, like a loaf of bread, it's really the elements near the surface where we have the greatest reduction in humidity. That reduction in humidity means we're going to have the greatest shrinkage. That means we're going to have the greatest stresses. And in addition to leading to cracking, this can actually lead to curling in these slabs, which can be very dramatic. So shrinkage reducing admixtures can really be effective either integrally mixed or topically mixed because they're really going to have an impact on this moisture gradient. And to really try to illustrate this, we've used some results from neutron radiography tests where they show two things. We have a plain water system, a plain concrete here shown in the center, and we have a shrinkage reducing admixture system shown here over on the right hand side. And what we notice is there's two differences when you have water or SRA in the system. The first thing is the water system loses not only water near the surface into a deeper depth than the shrinkage reducing admixture, but the second part is it also sucks more water out of the core of the sample than we have with the shrinkage reducing admixture because of the high capillary stresses in the system. So again, the two differences are a deeper curing affected zone, a deeper curing profile, and more water being drawn out of the center of the specimen. And what this leads to is a lot more curling in a plane system than we see with a system that has a shrinkage reducing admixture in it. Now, the third basic item that we wanted to really talk about with shrinkage is we often talk about the free shrinkage of our concrete. How much does it shrink if it's not restrained? However, this really isn't enough to describe what people really want to know in practice, which is will the concrete crack when it's placed into our structure? So, all too often we see bridge decks. This is a high performance bridge deck that was placed and touted as being a very long lasting concrete. But you'll notice that there are cracks here about every 2/3 of a meter that really develops because of the shrinkage in the system. So while unrestrained shrinkage is interesting, it really doesn't tell us the whole story. And this can actually help us to now start to motivate the fact that it's not just the free shrinkage, but it's an interaction with other properties that we need to start to consider when we start to consider how susceptible a mixture may be to cracking. So we may take students through the idea that we have an initial specimen. That initial specimen will want to shrink, but because of the restraint, we're actually going to pull that specimen back to its original displacement. And we can start to talk about the stresses that would form due to Hooke's law and due to the elastic modulus in the system. So we can now talk about the elastic modulus. We can talk about the time dependency here, and we can actually show that we could compute the stresses that would develop if this was a completely elastic system. Then we can start to get into the fact that under stress, concrete would creep, or we could even think about this as relaxing because we have a constant displacement and would actually reduce the overall stresses by this relaxation force shown here by this little purple arrow. And we would now be able to start to introduce the idea of viscoelasticity, which can be very high in these systems at early ages, that leads to an overall state of stress. So the idea now is we can calculate the elastic stresses, but we'll know that stress relaxation Microcracking can reduce these stresses in the overall system. And what we really worry about is the built up stress here shown by the blue line. Now, we're going to want to compare that stress to the strength of the concrete. And whenever that stress exceeds the strength of the concrete, we're going to have cracking in the overall system. So we can use these simple types of modeling calculations to really start to show the impact of various properties on the cracking behavior. So a stiffer system means it's going to be more likely to crack. Things like that become very interesting for students to be able to look at and to try to understand. We can also start to discuss the idea that there can be some very simplistic tests that we can use to describe this behavior. So there's been a lot of work done with uniaxial hydraulic machines that hold a zero displacement, and Rilem has really been a leader in bringing that work to life. But for about 100 years, there have been groups that have been using a simple restrained ring, and the idea here is you have a piece of steel. That steel is instrumented with a few strain gauges. Concrete is cast around that steel ring. That concrete wants to shrink and get smaller. The steel prevents it, and the steel is going to have a strain that builds up. That strain is going to build up over time, and at some point, that strain releases, and it releases because a crack starts to form inside of the concrete. Now, you can actually use the strain that's been produced in the steel, and you can calculate the fictitious pressure that's required to generate that strain in the steel. You can then, by knowing that fictitious pressure, you can turn that around and you can say, here's the pressure that's acting on the wall of the concrete. And you can solve this to determine the overall state of stress that's inside of the wall of concrete. Now, the really interesting part about this is you can actually now compute the state of stress that's inside of the concrete at the highest point at at the inner radius, and that's going to be equal to the strain measured in the steel times a whole bunch of constants that will be described by the overall standardized geometry of the specimen. So whether it's the geometry of the concrete, whether it's the geometry of the steel, or whether it's the elastic modulus steel, this again is something that's very simple for students to calculate, and you could run this with different size steel rings so you could look at things like different degrees of restraint. Now, the real takeaway for shrinkage reducing admixtures is when we have plane systems, those plane systems can crack, and they can crack at very early ages. So here we see a zero point 0.5 water to cement ratio. We see earlier cracking with a zero point 0.3 water to cement ratio because the higher strength materials are more susceptible to cracking. And not only are they more susceptible, but when they crack at an earlier age, the cracks tend to be wider because we haven't relaxed out more those shrinkage stresses in the system, shrinkage strains in the system. But when we add shrinkage reducing admixtures, and this is about 5% by weight of water, what we notice is we can get these to a point where they don't crack. And after a certain point, they just will never crack because the stresses aren't rising. So one out of the six rings here cracked when we were using shrinkage reducing admixture, where all six cracked at a very early age in the plane system. This clearly starts to show the benefit of the shrinkage reducing admixture. In addition, what I want to point out is the single ring that we talked about before may not be completely sufficient to describe all of these systems. So we've actually moved to a dual ring, dual restrained ring. We have an inner ring that handles the shrinkage. We have an outer ring that handles any expansion. And with things like shrinkage reducing admixtures, internal curing, expansive agents, we almost always see an expansion in these systems. The other real benefit is when we make these rings, we now make them out of Invar, which means that they're really not susceptible to temperature change. They maintain a constant volume as the temperature changes. So we can place them on heating and cooling plates, and we can, at some age, we can now start to change the temperature of the ring, and we can really look at the impact that has on stress development and what's the residual capacity that's left inside of our concrete. So we can run these tests and we can essentially assess the residual capacity at much earlier ages to see how susceptible a concrete sample may be to cracking. Now, one of the final things that I want to talk about with the restrained ring test is the impact of the boundary conditions. When a sample dries from the top and bottom, the state of stress is always has a stress field of 1 over r squared. However, when the ring dries from the outer circumference, end up with a very complicated stress field where we have a very high stress level at the outer edge because we're getting a lot of moisture diffusing out of from the system, and then we get a high stress at the inner edge because of the geometry effect, and the shape of this changes throughout the entire time of drying. Now, while we can solve equations for both this expression and this expression, it's much easier to go through and simply use the top and bottom drying because the stress field always remains the same shape, and it always scales as 1 over the radius squared, with the highest stresses at the inner surface. Again, a lot of the real valuable work that happened in early age concrete, early age cracking, shrinkage reducing admixtures, internal curing was really taking place at the end of the 1990s and going into the early 2000s. And Rilem was a leader in really bringing a lot of this information together in Technical Committee 181. And you can go and you can download this report, and it's a great read on a lot of the early age shrinkage that's taking place in these systems. And this committee was led by Arnon Benter, who is a former president of Rilem. And I think this is a really great document. And there's a great opportunity for you to get involved in Rilem committees to really see state of the art work that's going on around the world. One of the other things I wanted to mention is I mentioned very briefly that the stress is going to be the stress shown here in pink is going to be related to the tensile strength of the concrete. And when they intersect, we're going to see that they're going to crack. Now, it happens that in practicality, once the stress reaches about 80% of the tensile strength, we're going to get cracking. But this is really for an unnotched or an uncut specimen. Many times we're really worried about what happens when we have a sample that has either a tool joint or a saw cut joint inside of the system. And what we have to do is we have to take into consideration the stress intensity factor due to this saw cut that's inside of the overall system. So we use nonlinear fracture mechanics, again, another area where Rylem's really been a leader, to calculate how much you would reduce the strength of the section by how deep the saw cut is inside of the sample. So if you have a saw cut that's a third of the depth of the slab, which is very common, you decrease the stress to about 30% of the original strength, and that now becomes the failure envelope. So if you're before this point, you reach this point, you have stable crack growth, and you can control the crack with the saw cut that's there. Now, I'd like to briefly mention another example of what we can actually do with this modeling approach. So this equation that we're showing here is simply the equation I showed before where we were talking about the elastic component, the creep component, and the shrinkage that's taking place in the system. And what we're doing is we're going to be calculating the state of stress that develops inside of this restrained concrete element. Now, one of the things that we can do is we can actually do this very deterministically, and we can calculate the age at which the stress exceeds the tensile strength. However, we know that there's going to be some variation inside of the material properties. So what we could actually do is we could simulate what happens if there's some variation in the strength of the material, and what happens if there's some variation in the properties that lead to the stress development in the material. So these could be variations in the elastic modulus or variations in the shrinkage, for example. Okay. Now, if we start to do this, what we'll now notice is that the age of cracking is in a single deterministic point, but it starts to vary now, and we're going to start to get a distribution of the ages of cracking for our overall system. In fact, we may end up with systems that never crack. We could have it where the strength stays above the stress that develops inside of the system. So what we did was we used an approach called Monte Carlo simulation here, where we ran the simulation tens of thousands up to millions of times. And what we were able to do was we were able to plot the age at which the sample cracked using simple variations that we would expect from the material properties. So if we did this with deterministic properties, what we would notice is that this particular sample that we're simulating, this would crack at an age of about 28 days. So this is our deterministic solution. But as we start to place variation in the system, we notice that some of the earliest samples crack at around 7 days, where we can get to a point where some of the samples never crack. And we could take this out for a year, and we have a certain percentage of the samples that never crack. Now, we've done this with Monte Carlo simulation, although you could also do this with, with standard statistics with resistance factor design. But the really big takeaway from this really starts to change the way we think about designing our concrete slabs. So now instead of worrying about the age of cracking, right? What we start to worry about is the probability that our slabs will actually crack. So now we're starting to look at what's the likelihood that our slabs are going to crack in practice. And if we place 10,000 slabs for this example, 75% of them would crack. Well, what we really want to try to do is we want to try to reduce that probability of cracking down to a value that's like 5%. And what we're going to now go through is a design approach that you could actually use to do this for mixtures containing shrinkage reducing admixture. So the basic idea here is we've run those Monte Carlo types of simulations to simulate the probability of cracking for mixtures containing different amounts of shrinkage reducing admixture or different overall shrinkage strains in the overall system. So what we can see is in a plain system, maybe we're way out here, right, where we have a 95% probability of cracking. And if we wanted to reduce that probability of cracking down to 5%, we have to reduce the shrinkage from this value here that's about 3,700 microstrain for the paste down to this value down here, which would be about 2,700 microstrain. So we can see here that we want to make a reduction in the shrinkage. I think the most important part of this is we can actually now start to relate the shrinkage to the impact that the SRA will have on the surface tension inside of the overall system. And we can say, well, if we had our plane system, which is here, and we add SRA, we can calculate what the reduction in shrinkage is by the change in the surface tension. And all of a sudden we can say, here's where we'd be at with 5% shrinkage reducing admixture in the system. So there's two really important concepts here. One is we can now start to really relate the shrinkage to the surface tension and to a reduction in shrinkage. The second thing, though, that I think is also very important is the reduction in shrinkage is not linearly related to the reduction in cracking. So a very relatively modest reduction in the shrinkage, going from like 3,600 down to 2,600. So maybe we have like a 20 or 30% reduction in the shrinkage, is almost a 95% reduction in the potential for cracking. So we see here very, very huge benefits of reducing the shrinkage, even by 20, 30% in the overall system. Now, in addition to just looking at shrinkage and looking at cracking, there are some other properties that can be impacted when shrinkage reducing admixtures are added to the system. So what I want to be very clear on here is we're talking about the properties of the fluid. We're talking about the surface tension of the fluid. We're talking about the viscosity of the fluid. And while we reduce the surface tension, we can dramatically increase the viscosity of the pore solution. Now, increasing the viscosity of the pore solution is going to impact several properties. First, it's going to impact the diffusion coefficients and the diffusivity of water. So the surface tension is going to make it harder for the water to diffuse out of the system. We're going to have a higher diffusion coefficient as we start to change the surface tension, but we can also start to change the viscosity. And what we'll notice is as we increase the viscosity, we really reduce the diffusion coefficient, making it harder and harder for water to leave the system. So again, surface tension will impact the diffusion coefficient. Viscosity also impacts the diffusion coefficient. In addition to impacting the moisture diffusion coefficient, what we can notice here is that we can impact the diffusion coefficient for ionic species like chloride ions, for example. So on our left-hand side, we see just a standard diffusion sample where we've placed a de-icing solution, a chloride solution on top of a sample that contains shrinkage-reducing admixture. And what we notice is because we have a more viscous pore solution, we dramatically reduce the amount of chlorides that are going into our concrete. So what you can see here is at the depth of at a certain level of chlorides, we have maybe 5 millimeters more penetration in our plane system than we do with the shrinkage reducing admixture system, simply because of the viscosity. And if you think about this, if you were a chloride ion, swimming through water is a lot easier than swimming through honey, and that's why they're going to move faster in that system. But this behavior gets really amplified whenever you have not only diffusion, but you have diffusion on one side or you have ingress on one side and you have drying from the other side. So you have a classic case of wicking taking place here, where now all of a sudden you see both the effects of the viscosity and the surface tension because you're seeing a more dramatic impact of the shrinkage reducing admixture because it's also going to impact how the water is being drawn out of the system on the other side of the sample. The final item I just wanted to mention here very quickly is shrinkage reducing admixtures will also impact the rise of fluid inside of the system. So here we see a neutron radiography image where we have a fluid. That fluid will be absorbed into our concrete and we can plot the depth of the absorption. So here is the depth of the absorption Z, and that's essentially being plotted as the square root of time. And what we can see for a plain concrete is that depth of penetration can be very high. Now, if we start to use a shrinkage reducing admixture inside the system, we dramatically reduce the depth of that penetration. It's because we're altering the surface tension shown here as gamma, and we're altering the viscosity of the system. So we're making it more viscous and we're making it have a lower surface tension. So there's going to be less capillary suction drawing the fluid through the overall system. So, in conclusion, a few things that I really wanted to try to drive home. I think shrinkage reducing admixtures are a great thing to bring into the classroom because they really help us to start to bring out some of the mechanics of what's really happening in shrinkage and shrinkage cracking in these systems. We know that shrinkage is going to be related to the paste volume, the surface tension of the fluid, and the pore size are going to be all very, very important. And we can start to dispel some of the myths and we can start to say that it's really the volume of the gel pores that are important, not necessarily the water to cement ratio. Shrinkage reducing admixture reduces surface tension, but it also alters some of the other properties of the fluid. For example, it increases the viscosity of the pore solution. The change in surface tension is going to be linear related to shrinkage. However, it's really important to note that shrinkage is not necessarily linear related with cracking, and a small reduction in the shrinkage of the system can have a huge impact on the cracking and a huge impact on the curling of our concrete. So there could be really big value benefits with using shrinkage reducing admixtures. Surface tension and viscosity can dramatically impact transport properties, and we have to be very careful when we bring these into surface life models because they can dramatically extend the surface life of a concrete structure. And the final thing that I'm going to mention here is that everything that we talked about was the shrinkage reducing admixture replacing a portion of the water. And unlike other admixtures, SRAs should really be dosed by water because they're acting on the fluid part of the system. They're not necessarily acting on the cement particles like we see with things like water reducing admixtures. So SRAs should really be dosed based on a percentage of the water. Again, I really want to thank the Rilem committee for the invitation to do this, and I'm happy to take any questions that you may have.